Welcome to this video where we will see about an inexpensive thermoelectric generator device that harnesses the cold of space without active heat input and generating electricity that powers and LED at night. Scientists say this device is able to generate electricity at night, when solar cells don't work. They firmly believe that beyond lighting, this could be a broadly enabling approach to power generation suitable for remote locations, and anywhere where power generation at night is needed. While solar cells are an efficient source of renewable energy during the day, there is currently no similar renewable approach to generate power at night. Solar lights can be outfitted with batteries to store energy produced in daylight hours for nighttime use, but the addition drives up costs and expenses. Reliable energy access remains a challenge, particularly in off-grid regions throughout the world. While solar cells have enabled distributed power generation during the day, no comparable alternative exists at night. Here we will demonstrate a low-cost, modular mechanism of renewably generating meaningful amounts of electricity at night by harnessing the cold darkness of space. We use a passive cooling mechanism known as radiative sky cooling to maintain the cold side of a thermoelectric generator several degrees below ambient. The surrounding air heats the warm side of the thermoelectric generator, with the ensuing temperature difference converted into usable electricity. We highlight pathways to improving performance from a demonstrated 25 W/M2 to 0.5 W/M2. Finally, we demonstrate that even with the low-cost implementation demonstration here, enough power is produced to light a LED, generating light from darkness. The device developed by researchers overcome the limitations of solar power by taking advantage of radiative cooling, in which a sky-facing surface passes its heat to the atmosphere as thermal radiation, losing some heat to space and reaching a cooler temperature than the surrounding air. This phenomenon explains how frost forms on grass during above freezing nights, and the same principle can be used to generate electricity, harnessing temperature differences to produce renewable electricity at night, when lighting demand is at peak. Scientists tested their low-cost thermoelectric generator on a rooftop in Stanford, California, under a clear December sky. The device, which consists of a polystyrene enclosure covered in aluminized mylar to minimize thermal radiation and protected by an infrared transparent wind cover. It sat on a table 1 meter above roof level, drawing heat from the surrounding air and releasing it into the night sky through a simple black emitter. When the thermoelectric generator module was connected to a voltage boost converter and a white LED, the researchers observed that it passively powered the light. The voltage sweep shows a short circuit current about 44 mA and an open circuit voltage 79 mV. At the maximum power point, nearly 0.8 mW of power is generated by the thermoelectric module. Normalizing to the area of the radiative cooler, this corresponds to 25 MW/M2 of power generation capacity. They further measured its power output over 6 hours, finding that it generated as much as 25 milliwatts of energy per square meter. Since the radiative cooler consists of a simple aluminum disc coated in paint, and all other components can be purchased off the shelf, the research team believe that the device can be easily scaled for practical use. The amount of electricity it generates per unit area remains relatively small, limiting its widespread applications for now, but the researchers predict it can be made 20 times more powerful with improved engineering, such as by suppressing heat gain in the radiative cooling component to increase heat exchange efficiency and operation in a hotter, drier climate. Scientists say that their work highlights the many remaining opportunities for energy by taking advantage of the cold of outer space as a renewable energy resource. They think this forms the basis of a complementary technology to solar energy. While the power output will always be substantially lower, it can operate at hours when solar cells cannot. A large fraction of the world's population still lacks access to electricity, particularly at night when photovoltaic systems no longer operate. the ability to generate electricity at night could be a fundamentally enabling capability for a wide range of applications, including lighting and low-power sensors. Here, we demonstrate a low-cost strategy to harness the cold of space through radiative cooling to generate electricity with an off-the-shelf thermoelectric generator. Unlike traditional thermoelectric generators, our device couples the cold side of the thermoelectric module to a sky-facing surface that radiates heat to the cold of space and has its warm side heated by the surrounding air, enabling electricity generation at night. We experimentally demonstrate 25 MW/M2 of power generation and validate a model that accurately captures the device's performance. Further, we show that the device can directly power a light-emitting diode, thereby generating light from the darkness of space itself. Generating electricity through renewable means has motivated a wide array of fundamental and applied science and engineering over the past century. While photovoltaics has offered a viable commercial path to achieving this goal both at grid and small scale during the day, achieving small scale, distributed renewable power generation at night without storage remains challenging. This solar panel at night poses a particular challenge for the 1.3 billion people worldwide that lack reliable access to electricity, a population that represents a quarter of the developing world's population. Demand for electricity among such rural populations in the developing world is surging, with 3 applications in particular driving interest: cell phone charging, cooking, and lighting. Lighting solutions for resource-constrained, off-grid communities have drawn much global interest with a range of approaches implemented. Solar lights have made progress at this task but, as lighting demand peaks at night, require the coupling of photovoltaic or solar thermal modules to a battery, driving up costs. A modular way to generate electricity at night without the need for storage would thus have direct and significant implications for lighting applications. Beyond lighting, a broad range of low-power off-grid sensors could also benefit from a modular power generation source at night. Thermodynamically, for any energy conversion process to produce useful work, for example, electricity, there must be a hot source and a cold sink. Most renewable approaches to electricity generation, including photovoltaics and solar thermal systems, rely on using the sun as the hot source and the ambient surroundings of Earth as a cold sink. Using the ambient air surrounding Earth's surface instead as the heat source and space as the cold sink, then, would allow one to drive a new kind of nighttime heat engine and generate electricity at night. Remarkably, accessing the coldness of space is indeed possible through radiative heat transfer between a sky-facing surface and outer space. A significant fraction of thermal radiation from a sky-facing surface can pass through the atmosphere and reach outer space, enabling passive radiative cooling of the surface to well below the ambient air temperature. Early work on radiative cooling focused on evaluating materials for their ability to cool passively at night. More recently, subambient radiative cooling during the day has also been demonstrated through a range of materials strategies including photonic structures, metamaterials, and novel synthesis methods. On an energy system level, radiative cooling has been evaluated for a range of implementations, including for building scale cooling applications, and in conjunction with solar thermal collectors. While the ability to passively maintain a surface below ambient air temperature is useful, for applications such as lighting one needs to convert the temperature difference between the ambient and cold surface into usable electricity. One direct path to doing this in a modular and tractable way is to use a thermoelectric generator. Thermoelectric generators have attracted significant attention in the past 2 decades, with one line of inquiry seeking to use them to recover usable power from waste heat escaping a small-scale thermal system, such as that from a fire or stove. Considerable research is also ongoing to improve thermoelectric generator efficiency with a view toward both off-grid power generation and waste heat recovery at industrial scales. However, the vast majority of approaches using thermoelectrics for nighttime power generation require an active input of heat. Previous theoretical works derived the limits for generating electricity from Earth's net infrared emissions to space. Researchers experimentally demonstrate a simple, low-cost way of generating electricity at night based on a thermoelectric module that generates enough electricity to passively power a light-emitting diode, LED, at night. This system is entirely passive, that is with no active power input, and is constructed in a low-cost modular fashion. They characterize the system's performance under a clear night sky under varying loads. They then show that the system's performance can be effectively modeled using knowledge of the thermoelectric module's properties, the air temperature, and the atmospheric properties in the mid-infrared window where the sky is transparent. Finally, they show that the electricity generated is enough to power a LED. Thus, we generate light from darkness. Thus we can see the following results obtained from the experiment. 1. A thermoelectric generator is built whose cold side radiates heat to the sky. 2. Nighttime power generation of 25 MW/M2 is demonstrated, sufficient for a LED. 3. Pathways to performance is greater than 0.5 W/M2 using existing commodity components exist. 4. This approach is immediately practical for lighting and off-grid sensors. Having validated the thermal model, we can use it to predict the temperature difference between the hot and cold sides of the thermoelectric module in different weather conditions as well as through improved thermal engineering. To summarize, we have highlighted the remarkable possibility and potential of generating small amounts of power by radiative cooling at night using low-cost, off-the-shelf, commodity components, less than $30 USD for our initial proof of concept demonstration. In off-grid locations throughout the world, this approach of generating light from darkness highlights an entirely new way of maintaining lighting, entirely passively, at night. The power generated could also be used to power small sensors in remote locations, with their lifetimes not being limited by batteries but the lifetime of the thermoelectric module, which can be an order of magnitude longer. Unlike other approaches to ambient waste heat recovery using thermoelectric generators, including from human body heat or the mechanical motion of human walking, our strategy is not limited in scale by the human body's dimensions or the area of a particular source of waste heat. Thus, we saw how a thermoelectric generator, a solar panel alternative, can produce electricity at night. For more updates, subscribe to the channel. Thank you.